Hello my dear students, this is Akash HD. Welcome to the ASD physics classes. Hope so you all are doing really great. So students, in this video we are going to learn the basics of moving charges and magnetism. Okay, so let's learn all these things, then the things will be more clear. Okay, so see, here under the moving charges and magnetism, the introduction is, kindly see here, the branch of physics which deals with magnetism due to electric current or moving charge is called electromagnetism here. Okay, so in this chapter we are going to learn the magnetism that is coming from electric current or moving charge. Okay, in next chapter, that means magnetism and matter, we will learn this magnetic field and all due to the material here electric current, but there material, the property of the material like a dia, para, ferro will be used and we'll learn the magnetism, but here only and only electric current and the moving charge. That's why the name is what? Electromagnetism here. Okay, great. Now friends, let's see here the Oersted's observations, very important. Okay, so see here, Oersted observed that a current carrying conductor deflects the magnetic needle, or we can tell magnetic compass also, placed near it. Okay, so based on his experiments he has got a following observation. So to understand the basics, to clear the basics, we'll learn this Oersted's observations and all. Okay, so see here what kind of observations he has got here. The first observation is what's here: on increasing the current in a conductor or bringing the needle closer to the conductor, deflection of magnetic needle increases. Okay, that means what we can tell, that means strength of a magnetic field increases. Okay, so what we can tell here, students, here when the amount of current will increase, anyhow in the surrounding the magnetic field will increase. So we can tell here, as of now, magnetic field is directly proportional to current here. Okay, second thing, what is happening when the magnetic needle or magnetic compass is coming closer, that means observation point is coming closer to the current carrying conductor, so that time also field is increasing. That means we can tell very well here B is inversely proportional to R. Okay, as of now here. Okay, so when the magnetic needle will come closer, observation point will come closer, then the field is increasing here. Same is applicable when the reverse is happening. When the current will decrease, magnetic field will decrease, and when the magnetic needle will go away, in that situation also what will happen, the magnetic field will decrease. Okay, great. Now let's see here, the second observation is what's here: when the direction of current in conductor is reversed. Okay, now the direction, then deflection of magnetic needle is also reversed here. That means students, the direction of magnetic field is reversed. So from here we have got, anyhow the magnetic field is a which quantity? Vector quantity. Okay, so when the direction of the current will reverse, magnetic field direction will also reverse here. So what we are understanding here, the thing is that the value of the current will decide the strength of the magnetic field, and the direction of the current will decide the direction of the magnetic field. Okay, great. Now let's see the third one. See, we know also this basics, but see here, a charged particle at rest produces an electric field around it, while a magnet at rest produces a magnetic field around it. Okay, so these are basic things and all. Now charged particle at rest, only electric field. Next one, see here, a charged particle moving with a uniform velocity produces electric field and magnetic field around it. Both will come when uniform velocity is there. Next one, see, an accelerated charged particle, that means velocity is the non-uniform, okay, produces electromagnetic waves along with the electric and magnetic fields here. Okay, so charge at rest, electric field; uniform velocity charge, electric field, magnetic field; accelerated charge, electromagnetic waves along with electric field, magnetic field. Okay, now let's say sixth one, very important. See here, a current carrying conductor produces a magnetic field around it. What will produce? A magnetic field, but no electric field. Why? Because the conductor remains electrically neutral during the flow of current. Okay, remember that here, a current carrying conductor will only produce magnetic field and no electric field, because when the current will flow, whatever number of electrons will enter per unit time, same number of electrons will go outside also, na? Because flow of electron has to maintain. So at any instant the conductor will remain electrically neutral and it will not produce any electric field, it will produce only magnetic field. Okay, great. Now let's see the students, what is the magnetic field here? Okay, so magnetic field, let's see here, a region near a magnet current carrying conductor, we are seeing general definition, or a moving charge particle in which which effect, magnetic effect, not electrical effect, magnetic effects are observed is called magnetic field region of that magnet, current carrying conductor, or a moving charged particle. Moving charged particle here. Okay, so remember that here, which effect, magnetic effect. Okay, some important points are there, and before that kindly say here, this magnetic field is also known as, sometimes we'll use the word magnetic induction or the magnetic flux density also. This term we will use even in the next chapter also here. Okay, and see students, now some important points are there. First important, see, magnetic field is a which quantity? Vector quantity, as I have told you very well. SI unit, remember that here students here, Tesla. No? Tesla with Elon Musk, this name is very common, Tesla. After that, one more is this, Weber per meter square. I am writing the first full name, Weber per meter square. Okay, in short form we used to write here WB/m square here. Okay, so when we are using the short form, I will write here T, or will write here Weber per meter square here. Okay, this is called what? This is called here the SI unit here. Okay, great. Now students, if we talk about here the CGS unit here, okay, so CGS unit is what? The CGS unit is the Gauss, G-A-U-S-S, G, Gauss here, okay, Gauss, G will use here. And like here we are telling that the, like Weber per meter square, there it used to be the Maxwell per centimeter square, that we don't use it here, but okay, I am writing here, Maxwell per centimeter square here, na, in a short form, mx/centimeter square here, okay, but this Gauss is the very common, is it? Great. Now students, if we talk about here the next one here, SI and CGS unit relation here, okay, so remember that here 1 Gauss is equal to 10 to the power minus 4 Tesla. What is this here students? 1 Gauss equal to 10 to the power minus 4 Tesla, okay, and even you can write here 1 Tesla is equal to 10 to the power 4 Gauss, okay. But remember that here, na, because most of the time we have to convert from CGS to SIs. Na? So remembering this is the very important and beneficial also. Okay. Now students, let's see the next one, dimensional formula here. Na? So dimensional formula will be always written in a big bracket here. Dimensional formula, is it? How to get a dimensional formula? For that we should know some equation. As of now, remember that here, F equal to QVB sin theta. When the charge particle is moving in a magnetic field, it will experience the force. Later we will learn F equal to QVB sin theta. But what is B? B is given by here, students, see, B is given by F by QV sin theta. F by QV sin theta. Okay. So if I write here the dimensional formula, B is equal to force means, can you see here, MLT minus 2. Charge means what is this? AT. Velocity means what? LT minus 1. Sin theta, there is a no dimensional formula and all that here. Okay. So what will happen that here? Kindly see here. This is the M, and anyhow we can see here. See, this L and this L will cancel out here. Okay. And from this T minus will cancel out. So we can write here M, L power 0, T power minus 2. Correct now? And A power minus 1 here. Is it? This is the dimensional formula. You can check out, but maximum this will be correct only. M power 1, L power 0, T power minus 2, and A power minus 1 here. Okay, great. Dimensional formula, na? Remember that here. Next one is students, we'll talk about here this one here. What is this? Magnetic field lines. Just like electric field lines around the conductor, na? Or the non-conductor. Similarly, here also, what will be there? The magnetic field lines will be there. Okay, so see here the students here. So see, in order to visualize a magnetic field graphically, Michael Faraday introduced the concept of field lines, in short form MFLs. Okay, so you know very well, this is the North Pole, this is the South Pole, is it? The magnetic field lines will make the closed path here. Okay, so what will happen here inside the magnet anyhow? It will be like this here. Let me change here the color. Okay, so see, inside the magnet it will be like this here, is it? Like this here. Inside the magnet like this here. And if we draw here the directions inside the magnet, where to where? You can see south to north pole here like this here, is it? And outside the magnet, where to where? The north to south pole here, is it? And they are making what? They are making the closed curve. So based upon this, we can just tell these rules and all that. So see the students, the first property is what here? See here, the property is what? MFLs are closed curves. Anyhow, outside north to south, inside south to north, here is it? The closed curve will be there. Second one, see, outside the magnet, MFLs travel from north to south pole. While students inside the magnet, MFLs travel from south to north pole here. Okay, remember that here. All these properties we know very well here now, but this is the introductory video, so we are just learning that all this. Now see here, the MFLs never intersect each other here, now just like EFLs, MFLs will also never intersect. Okay, next one, see, MFLs emerge or enter in the surface of a magnetic material at any angle. Just like a electric field, you know very well, electric field lines are always perpendicular to equipotential surface. They will make 90 degree, but here not like that. They can enter or exit at any angle, no problem. Okay. Fifth one, see, MFL exists inside every magnetic material. Remember that here. Because electric field lines never exist inside the conductor. They exist inside the non-conductor now when it is charged here. But MFLs will always exist every magnetic material here. Okay. See next one, see sixth one. At any place, crowded MFLs represent a stronger field, while distant MFLs represent the weaker field here. Okay. And the seventh one, very very important, can you see here? Straight and equidistant MFLs represent a uniform electric field here. Okay. So if in case I draw here, let's take for example, say let's take like this here, straight and equidistant. Let's take like this here. See, I have drawn here. So what is happening that here? This is the uniform magnetic field here. What is this? Uniform magnetic field. That means if I write here, see, this is for example point M. Okay, and somewhere here I have taken point N. So what will happen that here? Magnetic field at point M and magnetic field at point N will be same. Which kind of field? Uniform magnetic field, straight and equidistant. No? Approximately. No? Diagram is there. No? See here. Next one, if we talk about like this, let's take this kind of field is there. See, let's take this kind of field is there. So here what is happening that here? They are not straight, they are not equidistant. So let's take here M and here N. Which kind of field here? Yes, the non-uniform magnetic field. Non-uniform magnetic field. And here, where the field lines are very close at point M, that means we can tell very well the magnetic field at point M is greater than point N here. So uniform magnetic field, straight and equidistant. Non-uniform magnetic field, that kind of property is not there. Okay, so kindly see very well. So students, I hope so this introductory video of moving charges and magnetism very very clear to you. Keep studying, keep growing.